Okay, this week we are going to talk about the system dynamics, and we are going to cover the basics and its notations and etc. Before we talk about system dynamics, let me cover the causal loop diagram first. This causal loop diagram can be seen as a basic building block or the conceptual design of system dynamics models. As it says, the cause and loop will impact the variable fluctuations, and that fluctuations can be modeled and be executed in terms of the system dynamics model. However, this causal loop diagram provides its abstract view or like design view of such models. So causal loop diagram, for example, like this, can be seen as a one modeling and simulation approach to model various factors and, more importantly, relationships between the factors. Okay, these factors are numeric variables or indicating the amount of the strengths. For example, here there are variables listed up here and here. And here, and here, and actually each node of these linkages, okay? These are the variables, factors, and the relationships are being represented as a link, okay? Link here, 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 okay? So these relationships are actually the feedback links. And there are feedback links which are going to be positively impacting the variable relationships. For example, net gains for A, I don't know, I'm not going to specify whole this scenario, but these are full. However, what it says is this. So net gains for A, if it increases, then individual A's activity will increase as well. Okay? Why? Because there is a positive link here. There is a positive link here. And the individual activities and net gains will also increase, like this. And there is a loop. What is it? So going up here, going down here, and there is a loop, and it's a positive feedback link. And here we say positive causal link. Okay? The two nodes or factors change in the same direction. Okay? And or otherwise, there are some other links which are being called negative causal link, which will impact, for example, let's say here, total activity, if it goes up, then here it says minus. It specifies minus here, and if total activity goes up, then gain for individual activity coming from this effect will lower this factor to a certain degree. That is being specified from this causal loop diagram. Okay, from total activity to the gain per individual activity. There is a link, causal link here, and it is being specified as a negative causal link. And if the source's impact is being increased, then the destination's impact is going to be decreased, right? So this is a pretty much conceptual model. This conceptual model will specify how the variables will fluctuate over time, right? The causal loop diagram is going to be consist of factors and the positive or negative causal links here. So this is a negative causal link, right? And this is positive causal link, right? And here, even though we have only factors and the causal links, what they are making up is the loop. So here, we are going to talk about the loops, and we have one loop here, it says B, and we have another loop here, what it says here is R. So we are going to call it balancing loop or reinforcing loop. Okay? So the positive and negative or negative causal links will create loops. First, we are going to talk about the reinforcing loop. Here, let's see this. So this is one simulation. Because this is very simple, I want to talk about this. This is a word of mouth case. What word of mouth means is that it's spreading a certain product or certain markets or certain goods or products values, and the word is spreading, right? So population is talking about that, and now it's being more popular than the yesterday. Okay, and what it says here is that word of mouth will have a reinforcing loop. What it says is that adoption rate will positively impact adopters because that people are talking about, so there is a spread speed, and that is being modeled by the adoption rate. And if adoption rate goes up, then adopters will be increased because that the word of spreading speed is being increased. And adopters as being increased, its followers, the adopters are being increased, means that the spread speed will be increased further, and that is being here modeled as positive as well, here and here. So this is getting a snowballing effect, so that what we are saying here is our reinforcing loop. Reinforcing loop. If a certain node is being increased, then after the loop, one ends up with the same result with the first increased loop. So as adopter rate increased, adopters were increased, and at the end of the adoption rate is again increased. So it's being reinforced through this loop. That is the nature of the reinforcing loop. And we have a balancing loop, which is another different type of loop. Here it is being specified as B. And what it says is this. So as adoption rate goes up, and it will impact negatively in terms of the potential adopters. So let's say that we have 100 of people. If adopters, the number of adopters going up, then 100 minus adopters will be the potential adopters. Okay? So that total population minus adopters will create this potential adopters, meaning that if adoption rate goes up, then number of potential adopters will go down. Okay? So let's say that there is these spreaders and going outside and talking to other people, and suddenly they found out that all these other target populations are also adopters. Then it means that new adoptions are less likely, meaning that adoption rate will go down. So that mechanism is being specified as this loop. As the adoption rate goes up, the potential adopters, number of the potential adopters will go down, and as the potential adopters decreases, the adoption rate will also being decreased. Okay, so here adoption rate is being affected by this reinforcing loop. However, on the other hand, it is also being affected by what? This balancing loop. Okay, so here balancing loop will be created by this negative feedback. So that's the only difference compared to the other case. And this is occurs writing odd number of negative links will create it. Okay, what if the even number of negative links means that negative link going down, however that being negative will again negative, what if then it's going to be increased further. Okay, so negative on negative will end up making increasing reinforcing effect. However, the odd number of negative links will create this balancing loop. Okay, so we are going to create a reinforcing loop or balancing loop through the combinations of the positive and negative causal links. And what we are going to do is seeing these fluctuations over time. However, that is for the system dynamics, and causal loop diagram is providing this kind of thought experiment framework.